Hello good people, Magnet B here. Welcome to my channel. This channel is all about learning on how to work online, the various jobs you can specialize in working online, the job that best suits your talents and capabilities. So if you are new to my channel and you like this content, you like to be learning more on working online, kindly consider subscribing and clicking that notification bell so that you don't miss a thing each time I upload new content. Welcome people. In today's video I'm going to discuss on how to handle mathematical questions in transcription. In the previous video, we said numbers above 10, we write them in numerics, and below, we write them in words. But in the case of mathematical transcription, all the numbers are written in numerics. For the main transcription companies that I've worked for, they all agree on this, that on mathematical equations, we write them in numerics. So guys, today I'm going to screen share on how to get started on mathematical equation. Before we get in the video, for transcription, captioning, and article writing training, contact me by this number here. WhatsApp me, give me a call, so that you can solve all those problems in transcription, captioning, and article writing. Guys, give it a shot. Hello guys, this is a sample of a mathematical job. So the first thing to do, click on guidelines, so that you can get to see on what we are required to do with this job. So as you can see, the most essential thing here is, in addition, make sure each speaker change is separated by a dash to signify speaker change. So make sure from one speaker to the next you use a dash. And again, we have been provided the audio tags. Another very essential thing about audio tags, when you are provided audio tags and you have not been told from the guidelines to use them, as long as they are provided, make sure you use them. In another case, you've been told in the guidelines to use the audio tags, but they're not provided when you open the video or the audio in that case. Make sure you don't use them. So what directs you on whether you are going to use the audio tags or you are not going to use them is the availability in the platform. So this is an example of a mathematical job. Let's give it a shot, guys. Control space to play the video.
They're all different, but they can't be very different. The most different they can be is to differ by adding in a constant. And this one isn't very interesting.
As you can hear, the speaker said "and." In Verbit, in clean read, we don't start a sentence with "and." So that's why we've deleted the "and" part and we have started this one.
This one isn't very interesting because this one would not be a geometric series. If it said 73 plus x squared plus ... Well, the first couple of ratios are different from each other. But this one and this one both give me geometric series. They both give me geometric series where the common ratio is x, but they do differ because this one starts with geometric series where the common ratio is x, but they do differ because this one starts with x and this one starts with 1. So the formulas for the sum of the geometric series give me something slightly different. So these are two different functions that have the same derivative.
So is it that
So as you can note, there is a speaker change here. So that's why I use the dash and then we start a new paragraph.
So is it that 1 is just the constant, I guess, in this case, or
Derivative.
so is it that 1 is just the constant, I guess, in this case, or
Which one? This 1 is there from the formula for a sum of the geometric series. This one is here because it matches this.
okay?
And that x is there because that's the initial term for this series, geometric series.
Mhm. Okay. I think I'm just trying to figure out how you can get this derivative.
Yeah, you know what? These two functions look...
You know what, in this case it's not a filler word because the speaker asked the question and then answered the same question.
You know what? These two functions look so different. You'd be surprised to see that they have the same derivative. But on the other hand, I invite you to do this. If you look at the difference between these two functions, here's one of the antiderivatives that I proposed. Here's the other antiderivative that I proposed.
When you search on Google, you can see there is no hyphen. So we delete it.
Antiderivative that I proposed. If you look how much they differ by, well, they have the same denominator, so just combine the numerators and you realize they differ by, well, they have the same denominator by, well, they have the same denominator, so just combine the numerators and well, they have the same denominator, so just combine the numerators and you realize, oh, these two functions just differ by a constant. So they have to have the same derivative. Ah, cute, huh? And let's face it, it's easier to get the derivative of this one. I'll show you in a second. It's easier to get the derivative of this one because you don't need the quotient rule. Here you need the quotient rule, and it looks like you have to do more work to compute the derivative, but you're going to get the exact same derivative as you will for this guy, and that's a lot easier to compute.
This sentence is not complete. And
but you're going to get the exact same derivative as you will for this guy, and that's a lot easier to compute. In fact, let me do it. I do want to move on with this one example. So now that I have formulas for different functions h that have this derivative equal to g, let's actually use them.
incomplete sentence.
Let's actually use them. Let's use this derivative, h of x, excuse me.
And then as you can see, there is a repetition here, and because it's green red, we eliminate one use.
Use this derivative, antiderivative. Antiderivative. H of x, antiderivative. So that's an antiderivative of g, and I know that by comparing the two power series. But write this as being 1 minus x to the minus.
Here's the place where the mathematical guidelines come into place. 1 minus x, it's a mathematical equation. So in this case, even though numbers below 10 should be in words, in this case we are going to use a numeric because this is an exception. 1
minus x to the minus 1 power.
To the means is a superscript. And we said when there is a superscript and a subscript, we use an underscore. So in this case, to the, you delete this part like that, then use an underscore.
X to the minus 1 power, that makes it
Numerics.
1 power, that makes it very easy to compute its derivative. H prime of x is equal to negative 1, that's the exponent. Bring down
Equals to negative 1.
1, that's the exponent. Bring down the exponent, decrease the exponent by 1. Don't forget to multiply by the derivative of what's in by 1. Don't forget to multiply by the derivative of what's inside because chain rule. And that tells you that h prime of x is 1 minus x to the minus 2.
The same case here. To the meaning is the superscript.
2. But h prime is what is supposed to give us g. So it looks like I've got now a formula for what that function g is. Function g is this function right here. It's a power series. 1 plus 2x plus 3x, etc.
1 plus mathematical equation.
1 plus 2x plus 3x, etc. It's a power,
In Verbit, exact we know it's in etc.
etc. It's a power series, and it converges for some values of x. And for all those values of x, what it's going to add up to is exactly this quantity. In particular, I know what happens if I plug in g equals a half.
And another thing, fractions. Always use words. When it says half, use words.
A half. So this is a half. You raise it to the negative 2 power, what you're going to get is 4. Negative 2 power, what you're going to get is 4. And then over here, when I said we're going to use that to calculate the value of the, we're going to use that said we're going to use that to calculate the value of the function f, well, that's supposed to be 1/2 of
caps. Use caps too.
Well, that's supposed to be 1/2 of g of a half. So now it'll be 1/2 of g of a half. So now that's going to be a 2. It's supposed to be 1/2 of g of a half.
And another thing, remember when the speaker says 1.5, use 1.5, but when he says 1/2, use 1/2. 1 with a hyphen there, half, like that.
1/2 of g of a half. So now that's going to be a 2. And I remind you what f of a half means, be a 2. And I remind you what f of a half means, if you lost track of f. F was this power series when you stick in x equals a half, you get exactly the series that I began with. You get exactly the series that I began with like half an hour ago. This is the sum of n over 2 to the n for all n greater than or equal to 1. Over 2 to the n for all
2 to the n, to the meaning raised to power n. So it's 2 underscore n.
n for all n greater than or equal to 1. Write out the first 1. Write out the first few terms longhand. That's a 1/2. Write out the first few terms Write out the first few terms longhand. That's a 1/2 plus 2. That's a 1/2 plus 2/4.
As we said, 1/2. And then if you can see in this case, the speaker means a half by saying 1/2. It's not 1.5, meaning it's not 1 and a half. It's 1/2, meaning it's just half. So use 1 hyphen. You can see
that's a 1/2. That's a 1/2 plus 2/4 plus 3/8. 2/4 plus 3/8 plus 4/16, etc. 16ths, etc. And of course that's a half. Etc. And of course that's a 1/2 and a half, so that adds up to 1. It's a 1/2 and a half, so that adds up to 1. Here's a little bit more than a quarter. That's a quarter, so those add up to more than a half. And you see you're sort of building your way up to a sum of 2.
Sort of is a filler word. And you can see you're building your way all the way up. It makes sense without the sort of in a sentence.
You're sort of building your way up to a sum of 2. So that's the conclusion from all of this. Here was the series that I gave you 15 minutes ago, and I said, does it converge? And you quickly said yes. And then I said, what does it converge to? And you said, I had no idea. But we have an answer now. We know what it converges to. It converges to. And how did we get?
It's the same speaker.
And how did we get that little miracle? So here's the review. The way to get a sum of a series like this, if possible, is look for a way to think of this as being just one value of a power series. Somehow introduce an x into the problem that will have the feature that when you replace that x by some number, then you'll come back to the series that you started with. And now you've got a power series, and you have to try to figure out, well, what does that power series converge to? Can I do anything with formulas? And the answer is, nah, it's not always clear that you can. But now that there's variables in there, now that you have, now that there's,
as you can see, this is an incomplete sentence. The speaker said, but we, and then started a new sentence, now that. So in this case, because it's in plain read, we delete the first part. But now that there's variables in there, now that you have functions, you can start to use the tools from calculus. And that's what I did here. I started to use the idea of multiplying out
two functions, two power series, two polynomials is what it looks like. I talked about anti-differentiation of polynomials.
There is an hyphen.
Anti-differentiation of polynomials. I talked about differentiation of polynomials. Of power series. And polynomials. Of power series.
Because it's green grid, we delete the first part. Just like that.
Differentiation of polynomials. Of power series. And in that way, I find that I could actually work my way back to a geometric series. That's the advance that made it possible for us to get some number out of this. Somehow, by using those calculus tools, I managed to get down to a geometric series. A geometric series is something that I know how to. Geometric series is something that I know how to add. I know what the sum is for a geometric series. So anything that I can do that starts off with the fact that this geometric series adds up to this formula. Take that one equation and differentiate it and anti-differentiate it and multiply by things, and divide by things and stick in values for x. All of those steps will then give me more information about infinite series. What are we up to, 11.6? In this,
as you can see, what are we up to is a question, right? But we said numbers, when they begin a sentence, even in the above 10, we use words. But in this case, because it's a decimal, we are going to use numerics, even if it's starting a sentence.
11.6. In this section, this trick has to show up somehow. You have to somehow be using the fact that there's a geometric series, and a geometric series is something whose derivative you know.
You know, it's a filler word, but in this case, it's not a filler word.
Derivative you.
Also be the integral. So
Speaker change.
so
Say again?
Speaker change. This is not a question. This is not a question, it's just a statement. So use a full stop. Integral. It looks like it.
Say again?
can we also find something that we know the integral of?
I don't know what you mean by that exactly.
So like, instead of having it where g of x is equal to the derivative of another function, could there be a situation where g of x would be like the integral of another function?
Yeah, so
The integral of another function. The integral of another function.
A miss here. This a miss here. Integral of another function.
yeah, so yes, kind of. Let's do another example. Now this
Kind of is a filler word. It has been removed.
Let's do another example. Now this one is a little frustrating. So here, suppose that I gave you this series. And I said, guys, I want to put the n a little differently. What if I ask you?
Wanna, we change to want to in clean grid.
I want to put the n a little differently. What if I ask you for 1 over n times 2 to the n?
1 over n, 2 to the, meaning superscript, to underscore n.
n. Now the n is in the denominator. 2 to the n. Now the n is in the denominator. Okay, it's a series. You can easily show that it converges. Then, of course, the question is, what does it converge to? And you say, I don't know. Then, of course, the question is, what does it converge to? And you say, I don't know. And I will try to find a solution to that in the same way as before. So I'm going to say let f of x be this power series. Let's take 1 over n times x to the n.
1 over n, that's x to the, meaning superscript.
N. Then this thing right here becomes the value of that function when x is equal to a half. So if I can just get some sort of formula for what this function is as a function of x, then I'll just plug in x equals a half and I'll be done. So I don't know, what am I going to do this time, starting when n is 1? Now, what am I going to do when n is 1? So I've got x to the first power over 1 plus x squared 1 plus x squared over 2 plus x cubed over 2 plus x cubed over 3 plus dot dot dot. 3 plus dot dot dot. Well, what do you know about this series? It's not a geometric series. This one's not a geometric series. Previous ones weren't either, not right away. To get from here to here, I got to multiply by x over. Get from here to here, I got to multiply by x over 2. To get from here to here, I'd have to multiply by what, 2/3 of an x, and then next I would have to multiply by 3/4 of an x. So the ratio between
very essential.
quarters of an x. So the ratio between two consecutive terms is not constant. So that's not a geometric series. On the other hand, you could take the derivative of this. That would give you 1 plus, the derivative here is just
1
1 plus, the derivative here is just,
oh,
the derivative here is just x. The derivative here is just x. The derivative here is just x squared. And you get the pattern, right? I mean, if you just look at this formula.
In this case, right has been used to ask a rhetorical question. Hence, it's considered a filler word.
Pattern, right? I mean, if you just look at this formula right here with the sigma notation instead.
And again, Greek words, all of them, they start with a caps. For example, sigma, beta, alpha, and the rest. So in this case, we start with a caps like that. Control K is a shortcut when you want to change to caps or to small letters.
Sigma notation, instead of writing out all the terms, I really would like it if you would write out all the terms, or some of the terms, but if you just leave it in this form, then it's clear that f prime of x would be, the derivative of a sum is the sum of the derivatives, right? So I would just differentiate each one of these things separately, but the derivative of x to the n is n times x to the n.
X to the n.
N is n times x to the n minus 1. X to the n is n times x to the n minus 1.
We are done. I guess now you can see on how to handle mathematical equations in Verbit. And how to get started, guys. Give it a shot. It's not that difficult. It's just an illusion. To submit, click on submit, and then the spell check will suggest some of the terms that maybe you not spelled correctly and stuff. So if you are sure about the term, add to dictionary. Thank you for watching my video to the end. It has been on how to handle mathematical equations in transcription. For transcription, captioning, and article writing training, contact me via this phone number here. Give me a call, WhatsApp me, so that you can sort all those problems in transcription, captioning, and article writing. Until next time, stay tuned for the next episode. Bye.